My name is Simranjit Singh and I am here to present an analysis of edge detection and edge linking techniques. This presentation is a part of my coursework in PhD for Thapar University. So starting with these slides, firstly we have to know that what is an edge. An edge is a significant change in intensity of an image. So look at this photo. This is an edge, this is an edge, this is an edge. And if I draw a graph of this, it will look like this. This is, you can see these peaks signifies an edge because this peak signifies a change. This signifies an abrupt change. This signifies not abrupt but over an interval time change. So these changes are the edges. Going further into edges, now these why these edges are useful. The goal of edge detection, you can see that this is a photo of, and these are the edges of the photo. Now edges are useful in many things like in security, face recognition, computer vision algorithms. These edge detection techniques have a use limitless. Now these are the type of edges that can be identified. This is a step edge. This signifies a change from this to this. It is an abrupt change. So if a image contain a noisy image, if an image contains a noise, the change will look like this. It is also called a thresholding technique because it is 0 or 1. From here it is 0, from here it is 1, and this is an abrupt change. In the ramp edge as defined, the change is also there, but the change is over a significant interval of time. Look at this. Look at this. It is not abrupt, but it takes some time to change. And if a noise is contained, it will look like this. In a ridge edge, the change is abrupt, but after an interval of time, it will return to its original position. This is an interval of time in this. This is an interval of time in this. A roof edge, the change is not abrupt, but over a significant interval of time, and it returns again to its starting point. If an image contains a noise, it will look like this. These are the steps in edge detection. First step is smoothing. Why smoothing is required? Smoothing is nothing but to smooth out some noise. If an image contains a noise, the edge detector operator will get confused and detect this noise as an edge because edge signifies an abrupt change in intensity, so does the noise. So the operator get confused that which one is an edge, which one is a noise. So it detects the noise as an edge. So in order to avoid these situations, we have to first smooth out some noise if an image has any by using some denoising filters. Second step is to enhance the image. Image enhancement techniques are limitless. You can take any enhancement operator like sharpening filters and other filters that can enhance an image. If an image enhanced, so does the edges. So it's good. Third is thresholding. Thresholding technique is nothing but it is also in this step the noise is also phased out. And the fourth step is localization. This step localize the edge points and links them. These are the classification of edge detector. Edge detector techniques are of two types. This is gradient based and this is Laplacian based. The gradient based techniques follow a first order derivative, and Laplacian based techniques follow second order partial derivative. This technique contains this Robert, Prewitt, Sobel, and Canny. This technique contains Mar, Hildreth, all zero cross. So the first order derivatives is calculated in gradient based technique. This is a gradient, this is a partial derivative in the x direction, and this is a partial derivative in the y direction. Gradient representation looks like this. And now the gradient is a vector, so it has some magnitude and it has some direction. On every pixel the magnitude and direction are find out. Based on these, edges are detected. Now the implementation of partial derivatives in the x and y direction are shown in this. You can see that this is a Roberts filter. What happens is that this is a partial derivative in the x direction. You can see that. Now there is no center pixel. If we look at the mask, there is no center. Look, this is the mask of a Robert operator, Robert cross operator. This is 1 and this is -1. So there is no center pixel. So where does the when I try to calculate these type of things, I will end up like this. If I calculate x, this and this, the approximation will be in this pixel. If I calculate, meaning if I apply the operator like this operator in this direction, I will approximate this pixel into this. If I apply in the y direction, the resulting pixel will be approximated into this. So it contains no center pixel. That's why this technique is not widely used. This is the first technique which is developed in 1963 by Robert, and this technique is the basic technique of gradient based functions. These are the two masks defined by Roberts. In the second and third technique, these are quite efficient as compared to Roberts, because these contain a 3 by 3 mask and this contain a 3 by 3 mask. What happens is that this mask in the x direction and this mask in the y direction are taken onto the image and a convolution is done. Now you will ask me, now what is the convolution? Convolution is nothing, taking these masks, placing it on an image, multiplying it with the pixels present on these image, and the sum of this placed in the center pixel is the convolution. Are you understanding my point? Convolution is nothing. Take this pixel, okay, I will show you an image. I will show you an image. Suppose an image is present like this. Now take the matrix 3 by 3, place it here. There will be pixels underneath it. Multiply these pixels with this and place the result at the center. The center pixel like this. Okay, these are the two. These contains the center pixel. That's why these are more efficient as compared to the Roberts. And this is the most efficient operator of all the gradient based operators. What happened in this operator is Canny defined that the other operators like Prewitt and Sobel are placed on an image, but the Canny operator used a Gaussian filter to smooth out the noise first and then apply a gradient based approach to get this result. And these result defined by Canny is the most efficient by any gradient based edge detector. Now second order derivative contains the Laplacian of Gaussian. This is also based on the same technique as Canny, but this is a second order derivative. Second order derivative, the, the previous techniques contain the first order derivative, and the second second order and the Laplacian-based technique contain the second order derivative. The second order derivative are sensitive to noise, but they are excellent edge detectors. Like this, it is a filter of simple Laplacian. This is a filter of Gaussian. These two are applied to an image and the result is exceptional. Most These are the most efficient techniques, and practically these are used greater as compared to other operators. This is a zero cross technique. What happens in zero cross is this is a zero cross, this is a zero cross, this is a zero cross, this is a zero cross. This technique just take edge where zero cross occurs. This is based on these simple technique. Now we have studied previously all the edge techniques and edge how these operator will give out the edge points. Using those operator we only get the points. Now we have to link these points in order to efficiently show that what are the edges. That there's why edge linking comes into picture. Edge linking just link the edges to show a clearer and very good view of all the edges that are taken. These edge linking techniques are divided into two parts. First is local linking and second is global linking. The local linking is based on the neighborhoods of the points. It based on this condition that x dash and y dash belongs to a neighborhood if the function of x y minus the delta of x dash y dash is less than some threshold, and this technique is also good. Local edge linkers are not follow the similarity criteria. This similarity criteria is based on the magnitude and angles as shown in this slide. Now there is a global linker called an Hough transform. Hough transform is used in all the techniques, line detection techniques nowadays. It is based on a simple concept that the spatial domain here shows a straight line. When I change this spatial domain into a parameter domain by changing the equation, this straight line changes into a point in the parameter domain. So what happens if there are number of lines in spatial domain? What happens in parameter domain? As you can see, in spatial domain there are a number of lines intersecting at one single point. If I represented these into a parameter domain, it will take a single straight line. Based on this idea, if I reverse the role of a spatial and parameter domain like this, here I'm considering this straight line with only 2 points, just for the sake of assumption. These are the 2 points, x1 and y1, x2 and y2. When I represent these 2 points in the parameter domain, it will look like this. Intersecting at one point, the parameter domain will look like this. Now consider this line as a collection of points, mean x1, y1, x2, y2, x3, y3, x4, y4, y4, 3. Now this will contain into a Many lines, the points which are present here become lines here, intersecting at one single point. So based on this very concept, Hogg transform is formed. Hogg transform do nothing but map the spatial domain into a parameter domain, and if the lines are intersecting at, if two or three or four lines are intersecting at a single point, it means that this is a straight line in the spatial domain. Okay, like other method, it has also some limitations. First of all, the limitation of space and time complexity. Hogg transform takes a lot of computation power. It also requires a lot of space, and its output is not always correct. Thank you.